Hi everyone, this is Miss French with your first virtual lecture on Unit 3, Intermolecular Forces and Properties. The start of this unit is talking about the intermolecular forces that we touched on at the beginning of, or at the end rather, of Unit 2. So before we get into that, first I want to just get into a little bit of a difference between these two terms, intramolecular forces and intermolecular forces. An intramolecular force is a force within a molecule or within an ionic solid. These are more loosely defined as bonds. So your ionic bonds, covalent bonds, and even metallic bonds all count as intramolecular forces. And relatively speaking, these are all much stronger than the intermolecular forces that we're going to be talking about in this unit. Intermolecular forces are the forces between molecules, and you may also hear these called van der Waals forces. The first type of intermolecular force that we're going to talk about is dispersion forces. Dispersion forces are present in all condensed phases. This means they are not present in ideal gases, but they are stronger in liquids and solids. These forces happen because electrons are in constant motion, and at any moment in time, electrons can be distributed asymmetrically. So, just by random chance, these electrons have gathered for a moment over here, and that causes repulsion of the electrons in atom 2. That means that these two atoms become instantaneous dipoles, which means that they are just dipoles for a moment, and they are attracted to each other very weakly. So all molecules do this. Every type of molecule has dispersion forces. These are a relatively weak electrostatic attraction between the two species. And I do have a visual for you. This video is linked in another slide, so I'll make sure and let you know. But just this portion I'm going to play rather slowly. We can see that as this atom on the right is moving towards the atom on the left, the electrons are pushing the electrons away, and we have what's called the instantaneous dipole. Between molecules that have only dispersion forces, we can compare the strength of those dispersion forces. So there's two factors that can affect the strength of dispersion forces. We can talk about contact area, and we can also talk about polarizability. So let's talk about contact area first. These three molecules below are all C5H12. They all have the same formula. What's different about them is their structure and the arrangement and the shape. So in this first one here on the left, neopentane, what we see here is that it has the smallest contact area from molecule to molecule. This means it has the weakest attraction. In the middle molecule, the isopentane, this one has less surface area and therefore less attraction. And in this last molecule, the N-pentane, this is our longest molecule. It has the most contact area, so it's going to have the strongest attraction. And we see that reflected in the boiling point. Something to think about for boiling point is the fact that boiling a liquid means that the liquid particles will have to be taken apart, right? So we'll have to break the attractions between the liquid molecules to get them to be the gas, because the gas molecules are free-flowing and not attached to each other or attracted to each other. So in order to do that, you have to give energy, and the more energy, aka stronger attraction, will be a higher boiling point. The other factor we can talk about is called polarizability. So basically how easy it is for that molecule to become polar or get polarized. And we find that larger, heavier atoms and molecules are more polarizable. It has to do with the size of their electron cloud, but it also correlates with their mass. So as we look at the carbon family and the tetrahedral molecules that they will form with hydrogen, we see that CH4 has the lowest temperature at which it boils. This means that it's the least attracted to each other. Up here, SNH4, this is the heaviest molecule of the four, and it's going to have the highest boiling point. It's going to take the most energy to get those molecules to break apart from each other. We also mentioned pi bonding last unit, all that you need to know is that dispersion forces increase with pi bonding, and that pi bonding is found in double and triple bonds. So if you're comparing a molecule with single bonds to a molecule with double and triple bonds, you're going to say that the dispersion forces are stronger with that double or triple bond. And here's a link to that full video I was showing you. This is the Bozeman Chemistry Essentials on London dispersion forces. Now that we've talked about dispersion forces, we can talk about some of the other forces that are present. And this is going to be present when there are polar molecules. So if your molecule is nonpolar, it's going to only have dispersion forces. If you have a polar molecule that is in contact with a nonpolar molecule, then we call it dipole-induced dipole force. And this is a stronger force than dispersion. So the polar molecule is going to induce a dipole or push the electron cloud around until this nonpolar molecule becomes a little bit polar. And then there's going to be some attraction between those two molecules. We also have dipole-dipole forces. This is present between two polar molecules. The strength of these forces depends on the magnitude of the dipoles and their relative orientation. It's obviously a stronger force when the negative and positive ends are near each other. These forces are typically greater than those between nonpolar molecules of comparable size, and they act in addition to dispersion forces. So everything has dispersion forces. The next type of intermolecular force is hydrogen bonding. Hydrogen has to be bonded to one of these three very electronegative atoms: oxygen, nitrogen, and fluorine. And hydrogen bonding is a specific type of dipole-dipole force. So if we look at this molecule here, this is the water molecule. Hydrogen is present, and the hydrogen is bonded to the oxygen. So this would be an opportunity for hydrogen bonding. Water is our most common example and most important example of hydrogen bonding. Hydrogen bonding is the strongest of the dipole-dipole forces, but it is not stronger than our final force that we're going to talk about today, which are ion dipole forces. Ion dipole forces are present between ions and polar molecules. An example of this would be when we dissolve sodium chloride or salt in water, and the sodium and chlorine molecules, or ions rather, break apart from their crystal form and then start to interact and have attraction with the water molecules that they're dissolved in. This attraction is stronger than dipole-dipole forces. It's stronger even than hydrogen bonding. So in that dissolving example, those water molecules will be more attracted to the positive sodium and negative chloride ions than they are to each other. And you've heard of hydrogen bonding before. It is the most common intermolecular force that we talk about in biology. This is a blown up structural formula of DNA, and these hydrogen bonds are between the nitrogenous bases. They're what's holding the two sides of the DNA double helix together. Intermolecular forces affect the properties of solids. The most important property that we talk about is the melting and boiling point of solids and liquids. We know that stronger interactions between molecules will mean that it will take more energy or heat to break them apart. So if there is a high melting and boiling point, that will mean that there is stronger intermolecular forces. And similarly, weaker intermolecular forces will lead to a lower melting and boiling point. If we compare these three compounds, we have this compound, which has a lot of surface area to it, and then this second compound, which has some branching, and then this third compound, which has the most branching. So we're going to say that this top compound, based on shape, has the strongest intermolecular forces or strongest dispersion forces because it has the most surface area, and that's what's going to explain this high boiling point. This compound has the least surface area and that's what's going to explain its lower boiling point. We can also compare two compounds that have two different structures to them. So here we're comparing ethanol to methoxymethane. Again, we're going to notice that these two have the same formula, but their structure is different. In the ethanol, we have the oxygen bonded to the hydrogen. Remember, that's our qualification for hydrogen bonding. In methoxymethane, we have an oxygen and a hydrogen present, but they're not bonded together. So this is not going to have hydrogen bonding. We know that hydrogen bonding is a stronger force than dipole-dipole forces. So although these carbon to oxygen bonds are polar, this oxygen is going to have a bent geometry, so it's asymmetrical. That's where the polarity of this molecule comes from. The methoxymethane is going to exhibit dipole-dipole forces. The ethanol is going to exhibit hydrogen bonding. Hydrogen bonding is the stronger force. The boiling point of the ethanol is going to be higher than that of methoxymethane. Here's an example where we're comparing three different carbon compounds. Methane, CH4, is a nonpolar molecule. It's going to have only London dispersion forces. Chloromethane is a polar molecule where the carbon is bonded to 3 hydrogens and a chlorine. So carbon is in your center here. That's a polar molecule, so it's going to have dipole-dipole forces. And then the CH3OH, the carbon is in the center, bonded to 3 H's and an O. That oxygen is going to be bonded to a hydrogen as well. So that's going to have hydrogen bonding. And we can see that the strongest force, hydrogen bonding, correlates with the highest boiling point. Another property that we can predict trends for when we're talking about intermolecular forces is vapor pressure. Vapor pressure is the pressure that the gaseous part of the substance exerts on the container of said substance. So we need to understand that when we have a liquid, there is evaporation and condensation happening at the surface of that liquid at all times. And it's happening at the same rate in a closed container, and that's why we don't see the entire liquid eventually becoming a gas when we have the container closed. But because some of that liquid is becoming a gas, it's exerting a little bit of pressure on the container. If this liquid has molecules that are strongly attracted to each other, meaning that the intermolecular forces are high, then there won't be much gas above it, and it will have a low vapor pressure. If the intermolecular forces are low, it will be really easy for this liquid to evaporate into gas. There will be more gas above it, meaning more pressure. So our relationship then is that the stronger the intermolecular forces, the lower the vapor pressure. This one is an inverse relationship. The weaker the intermolecular forces, the higher the vapor pressure. Here's an example, excuse me, where if I look at something like water, water has the highest boiling point out of these 4 molecules. You also notice that it has the lowest vapor pressure. We would predict then that water has the highest intermolecular forces, or the strongest. And we could explain that by saying that the water has the most hydrogen bonding and is the most polar out of these 4 molecules. Here's a link down here in the slides to a Khan Academy example. I think this one is a video actually, to talk about the difference between vapor pressure, intermolecular forces, and boiling point. In this unit, we are going to see some particulate level representations, so I want to make sure that we all understand this symbolism. If you see a straight line between 2 atoms, that is showing a bond between the 2 atoms, and it is in the plane of the page. If we see a solid wedge between 2 atoms, that is also showing a bond, and it means that it's coming forward out of the page. And then if you see one of these dashed wedges, that's a bond that is going backwards out of the page. The other thing in this drawing that's really important to us are these dashed lines. Those dashed lines are trying to represent intermolecular forces or intermolecular attractions. The last topic that we're going to cover today is properties of solids. So some of this is review from last unit. We chatted a little bit about it last unit. Let's just go back over it. When we talk about the properties of ionic solids, the things that we expect to see are high melting and boiling points, because remember, these ionic bonds are the main force of attraction between these ions in the crystal, and so that's an intramolecular force, which is relatively stronger than all of the intermolecular forces. Because of those strong forces of attraction, they also have low vapor pressure when they're in their liquid forms. They're brittle, and this picture up here describes why they're brittle, because when their structure is disrupted, then the alternating charges are disrupted, and those charges repel, so we see a lot of breakage when pressure is applied to them. They also conduct when melted or dissolved, because once we do break down this ionic crystal structure, then we have charged particles that are free to move, and that's what causes electrical conductivity. Another type of solid that we talked about is the network covalent solids. Network covalent solids are made of nonmetals. They're either elemental, like carbon in its diamond and graphite forms, or binary compounds, like sulfur dioxide. They have high melting and boiling points. They're also really hard and strong structures, and they do not conduct electricity. Molecular solids, or covalent solids, have low melting and boiling points. They have higher vapor pressures in liquid forms. They do not conduct, and they can sometimes be large molecules or polymers. And then finally, metallic solids. We can expect to see good conductors that are malleable and ductile. Let's just talk for a few minutes about the differences between solids, liquids, and gases. Solids can be crystalline or amorphous, meaning that they can have a crystal definite shape or have no definite shape. In solids, their motion is limited. Their particles do not undergo translation, which means they don't move past each other. In liquids, the particles are in close contact and they are continually moving and colliding. Liquids and solids have similar volume because their particles are in close contact. This means they are not very compressible. And finally, gases. In gases, the particles are in constant motion. The frequencies of collision and average spacing between them depend on their temperature, pressure, and volume. Gases have no definite volume or shape, and they are compressible. Okay, that ends our first virtual lecture. I can't wait to see you in class. Have a great weekend.